Come on, my dears. Today we are going to begin chapter number 2, and the title of chapter number 2 is Electrostatic Potential and Capacitance. My dears, chapter number 1 was bit long. Similarly, chapter number 2 is also bit long, and the weightage of marks from these two chapters, from each of these two chapters, is 15 marks in the final examination. So both the chapters are very, very important. Come on. Section A, theoretical question answers. Okay, fine. Let us see first question. Question number 1 about line integration of electric field and some noteworthy points. My dears, in the textbook, in the beginning of this chapter, they have used one word so very often. What is that word? That word is line integration of electric field. But let us see now clear-cut explanation about line integration of electric field. What do you mean by that? Okay, I am showing you. Consider some arbitrary electric field. Arbitrary means at random, the way you like it. Okay, no problem. Here is some arbitrary electric field whose electric field lines are shown with the green colored arrows in the diagram. You should take care that no two electric field lines ever intersect. Okay, so keeping that point in mind, you may draw this figure. Okay, fine. Now in this electric field, we just select some arbitrary path. Arbitrary means at random, the way you like it, no problem. Here I am just choosing this sort of path, correct? This is the curved path from A to B. Now what do you mean by line integration of electric field over this curved path? Just to understand about that line integration of electric field, you just do one thing. You divide this entire path into extremely large number of extremely small length elements, and all those length elements are shown with these arrows. They are length element vectors. Length element vectors. You can see here is the first length element vector. Come on, second, third, fourth, and so on. Correct? So the entire path is divided into very large number of extremely small length element vectors. Got it? Fine. Now suppose we want to find out line integration of electric field from A to B. From A to B. That's why arrows are pointing from A to B this way. Correct? Fine. Now you may have a question that how much small should we take that length element? You should take each length element that small such that locally it can be taken straight. Not only that, at least for that particular length element, electric field can be taken almost constant. Okay, fine. Say this is ith length element vector, vector delta Li, correct? And in this length element, the almost constant electric field I am taking as vector Ei. Where is to be written this I? As a suffix, well below. Okay, fine. This I indicates order of length element, and that order changes from first to last. From first to last. Okay. Now you please do one thing. You take a dot product between these two. Dot product between electric field and length element vector. And similarly, you please take dot product like this only from first element to the last element. For first length element, come on, what is the dot product? Vector E1 dot vector delta L1. Similarly, for second length element, come on, vector E2 dot vector delta L2. Similarly, for the last length element, vector En dot vector delta Ln. Correct? And then after, you should take summation of all these terms. Correct? Then this entire summation, if you want to write in a single term, You may write mathematically this way, sigma vector EI dot vector delta Li, correct? You know sigma means summation, fine. Now, tell me, for each length element, how you can take electric field to be constant at all the points in that length element, provided length of that length element is taken infinitesimally small, that is extremely small, tending to 0. That is why I am taking limit delta L tends to 0. Limit delta L tends to 0. When you take limit delta L tends to 0, at that time this summation results ultimately into one specific integration, which is called line integration of electric field, and mathematically you can show by symbol integration vector E dot vector dl from A to B. Look, this summation is replaced by integration. You know sigma also will give you summation, integration also will give you summation. On the contrary, integration will give you accurate summation, correct? This electric field as it is, and when delta L tends to 0, we write the symbol vector dl, correct? And this term itself is known as line integration of electric field taken over the given path in the electric field. I repeat, integration of vector E dot vector dl from A to B is only known as line integration of electric field taken over the given path in the electric field from initial position A to final position B, correct? Fine. Now tell me, this whole term which is called line integration of electric field, you can rewrite this way also. You know vector E, it is nothing but electric field. In chapter number 1 we had studied electric field is going to give you resultant electric force exerted on a unit positive charge. Mathematically, vector E equals to vector F upon Q. Come on, vector E equals to vector F upon Q. Vector F upon Q, correct? Now tell me, did you study in 11th standard? This is nothing but line integration of variable force. And line integration of force is going to give you work done. So this numerator is replaced by work done, that is W, but that work is done on the path from A to B. That's why WAB, this Q in the denominator as it is. Okay, fine. So all these three terms, they indicate line integration of electric field. Now let us see some noteworthy points. What are the specialities of this line integration of electric field? Let us see one by one. First point, line integration of electric field is going to give you a scalar quantity. Why? You know dot product between two vectors will give you a scalar quantity, correct? So line integration of electric field gives a scalar quantity. Then second, SI unit of line integration of electric field. Let us find out. In chapter number 1, I had told you about two SI units of electric field. One was Newton upon Coulomb, another was volt upon meter. And what about unit of length element? It is meter. So volt upon meter into meter, meter will cancel, giving you volt. So SI unit of line integration of electric field is volt, shown by symbol capital V. And if you find out unit from this ratio, then it is the ratio of units of work to charge. For amount of work done, come on, it is joule, and for charge it is coulomb. So joule upon coulomb, joule upon coulomb. So volt is as good as joule upon coulomb. Simple. What does it give? What does it give? Line integration of electric field. Line integration of electric field gives us amount of work done on a unit positive charge when it is moved under equilibrium on a given path from initial to final position. I repeat, line integration of electric field over a given path chosen inside the electric field gives us amount of work done on a unit positive charge when it is moved on that path from initial to final position, keeping it under equilibrium. last time. Line integration of electric field over a given path inside the electric field gives us amount of work done on a unit positive charge when it is moved under equilibrium on that path from initial to final position. Simple. Fine. Then fourth point, on which factors does it depend and on which factor it does not depend? Come on, we will prove these two results in the next question, but at present you please remember, it is found that line integration of electric field depends on the initial and final position of the charge, but it does not depend on the path joining those two positions. I repeat, line integration of electric field depends on the initial and final positions of a charge, but it does not depend on the path joining them. Got it? And the same result we will prove in the next question. Okay? At present you please remember. And last point, suppose we move a point charge, say small q, from A to B, correct? Keeping it under equilibrium. Under equilibrium means with constant speed. And then after, we just bring it from point B once again to point A. In short, we just bring that charge back to its original position, correct? When you move from A to B on this path, and on another path when you move from B to A, you are coming back to the same point A. Means you are traversing over a closed path. And then if you take line integration of electric field over that closed path, we will prove in the next question that it comes out to be 0. Line integration of electric field taken over a closed path comes out to be 0. At present you remember this result. In question number 3, we will prove it. Okay, fine. I repeat, line integration of electric field taken over the closed path comes out to be 0. Correct? Fine. Come on now, we go for second question. And in that second question, we will prove one very important result. What is that? Prove that electric force is a conservative force and electric field is a conservative field. That is what we have to prove. Come on. Consider a source charge, say charge capital Q. It is a point charge. And if it is positive, you know its electric field line just go away from it. Correct? So electric field lines of electric field of this positive point charge are away from it, and they are shown in the diagram this way. Fine. Now in this electric field, we just choose two circular arcs. One is from A to C, another is from D to B, correct? One is from A to C, another is from D to B, right? For a given circular arc, its radii of curvature would be same. So whatever is this radius, RA, same is this radius, RC. So I am writing here RA equals to RC, correct? Similarly for this circular arc, come on, these two radii of curvature must be same. This one is RD and this one is RB. These two have to be same. So RB equals to RD, correct? Fine. Now just consider a test charge, say small q. This is source charge, capital Q. The small q is the test charge. And now this test charge is to be moved keeping it under equilibrium, means with constant speed. Fine. Now when this is moved with constant speed and it is taken from point A to point B, correct? You can just take it from point A to point B by traversing over various different paths. And out of various different paths, we just choose at this moment only two paths. One is from A to C to B, correct? A to C to B, A to C to B, that is path number 1, okay? And another path we will take from A to D to B, A to D to B, correct? Come on, path number 2 is from A to D to B, correct? So what we are going to do? We are going to move test charge small q from point A to point B over 2 different paths. Path number 1 is from A to C to B, and path number 2 is from A to D to B, correct? Now let us find out total amount of work done on both the paths separately, okay? First of all, we just divide this entire path into 2 parts. First part from A to C, second part from C to B, okay? Let us find out those partial work done separately. First of all, we go for WAC. According to formula, it is line integration of force from A to C, correct? From A to C. Here you may write vector dl, no problem, but we just go according to textbook. So instead of length element vector dl, here we are writing vector dr, okay? Now tell me, when you move test charge small q from A to C, look here, from A to C, correct, this way, then displacement is along tangent, and during that displacement, this electric field will provide electric force this way. So force is exerted this way, and displacement is in this direction. Force is along radius and displacement is along tangent. You know, for a circular arc, radius and tangent, they are always perpendicular. So this force vector and this displacement vector, this force vector and this displacement vector, they are right now perpendicular, and you know, dot product between 2 vectors which are perpendicular is always 0. So dot product between these 2 perpendicular vectors must be 0. That's why WAC is 0, because these 2 vectors are mutually perpendicular. Got it? Fine. Now we go for WCB. Fine. Now according to formula, it should be line integration of this force from C to B. Correct? Now this integration as it is, come on, vector A dot vector B, had it been vector A dot vector B, you could have written AB cos theta. Similarly here, F into dr into cos theta. Now take very special interest and try to understand why this theta is taken 180 degree. Try to understand. Look. When you move this test charge from C to B this way, correct? Keeping it under equilibrium with constant speed, displacement is in this direction, correct? But in order to move it under equilibrium, during the displacement from C to B, you need to exert constantly some external force which can balance this electric force. Because this test charge is also positive and this source charge is also positive. Positive charge will repel this positive charge this way. So electric force is this way, and if you want to balance that electric force, you must exert external force just in opposite direction. Correct? Equal in magnitude, opposite in direction. Now tell me, you are exerting external force this way, opposite to this electric force, and displacement is in this direction. External force is this way, displacement is this way, both are opposite, and you know angle between 2 vectors in opposite directions, it is 180 degree, correct? I repeat, when you bring this test charge here and then after when you move it from C to B, displacement will be from C to B in this direction. But during that displacement, you have to keep that charge under equilibrium, and for that you need to supply external force just in the direction opposite to this electric force. So I mean to say external force is in this direction, displacement is in this direction. because they are in opposite directions, angle between these two vectors in opposite directions has to be 180 degree. Got it? Fine. Now this integration as it is, come on, F equals to, according to Coulomb's law, K into product of magnitudes of two charges divided by square of the distance between them. K into product of magnitudes of these two charges, capital Q into small q, divided by square of the distance between them. When you move it, suppose you are here, when you are here, this distance I am going to show it by symbol R. So distance is R and it's a square. K into product of magnitudes of two charges divided by square of distance between them. Okay, fine. And this dr as it is, cos of 180 degree is nothing but -1. And now, along with this minus sign, because this k, q, q is constant, can be taken out of the symbol of integration. So ultimately minus k, q, q, integration from c to b, 1 upon r square dr. Integration from c to b, 1 upon r square dr. Correct? Now this part as it is, integration 1 upon r square dr is nothing but minus 1 upon r. How? Forgotten the formula? Integration r raised to n dr, what was that? R raised to n plus 1 upon n plus 1. Similarly here, if you take this r square in the numerator, it will be r raised to minus 2, and then if you take integration, then r raised to minus 2 plus 1 upon minus 2 plus 1, that is r raised to minus 1 upon minus 1, that is minus 1 upon r, minus 1 upon r. And now this variable is in terms of distance, so we must specify limits also in terms of distance. Distance of point C from source charge. Distance of point C from source charge, it is RC. So I am writing here RC. Distance of point B from source charge. Distance of point B from source charge, it is RB. So I am writing here RB. Correct? Fine. Now this minus minus plus K, Q, Q into 1 upon R from RC to RB. From RC to RB. Now place the limits. K, Q, Q as it is. You know how to place the limits. First of all, we are supposed to write the upper limit, and after putting minus sign, we are supposed to write the lower limit. Come on, substitute first of all upper limit. Instead of R, when you write RB, it is 1 upon RB, 1 upon RB. After putting minus sign, instead of R, we should write RC, 1 upon RC, 1 upon RC. Got it? But tell me, instead of RC, can I write RA? Instead of RC, we can write RA. Here it is. Instead of RC, I am writing RA, because RA equals to RC. Okay. Now, if you want to find out total work done on the entire first path, let it be W1, it is WAC plus WCB. Come on, WAC plus WCB, correct? But this WAC came out to be 0. When this is 0, put it here 0, then W1 will be equal to WCB. And that WCB is nothing but KQQ into bracket 1 upon RB minus 1 upon RA. KQQ into 1 upon RB minus 1 upon RA. Let it be equation number 1. My dears, this equation 1 gives us total amount of work done on first path. Correct? Now we go for path number 2 from A to D to B. First of all, let us find out WAD. WAD. Now this part AD is parallel to this electric field line. Earlier this part CB was parallel to this electric field line. Correct? Moreover, whatever is this distance, same is this distance, and whatever is this distance, same is this distance. So I mean to say, whatever is the work done on the path from C to B, same is the work done on the path from A to D. So this WAD and WCB, they are same. So you can write formula for this work done like this. Look here, KQQ into 1 upon distance of final point. Here 1 upon distance of final point. When you go from A to D, final point is D, so you should write here RD, minus 1 upon distance of initial point. minus 1 upon distance of initial point is A, so I should write RA, correct? Fine. Now this KQQ as it is, 1 upon RD, instead of RD I can write RB. Instead of RD, when I can write RB, just write it here. So 1 upon RB minus 1 upon RA, because RD equals to RB, correct? Fine. Now let us find out WdB. According to formula, it is integration of vector f dot vector dr from D to B, Now tell me, when you move the test charge from D to B, look here this way, at that time, at each position, the electric force and displacement, they remain mutually perpendicular. And that's why, because these two vectors are mutually perpendicular, the dot product between them should be 0. So this amount of work done is 0. Now we want total amount of work done on the entire second path, let it be W2. And then it will be WAD plus WdB, WAD plus WdB. But WdB is 0. When this is 0, just put it here, then W2 will be WAD, and that WAD is this much. WAD is this much. Same formula written here, same formula. Correct? Fine. Give it equation number 2. My dears, now compare equations 1 and 2. You can see right hand sides are same, and so left hand sides also must be same. That is W1 is equal to W2. In both of this formula, you can see amount of work done depends on initial and final position. Amount of work done depends on initial and final position. But it does not depend on the path joining them. Because in the first path, it was this path A to C to B. In the second case, it was this path A to D to B. Both the paths are different. Though paths are different, then also amount of work done comes out to be same. And hence, according to definition, electric force is proved to be conservative. Electric force is proved to be conservative, and hence electric field is also proved to be conservative force field. Remember from 11th standard, how did you define conservative force? If amount of work done by a given force depends on initial and final positions of a body, but it does not depend on the path joining them, then that force is called conservative force, and corresponding force field is said to be conservative force field. Remember? Similarly here, amount of work done by electric force depends on initial and final positions of a charge, but it does not depend on the path joining them. And so according to definition, electric force is conservative force and electric field is conservative force field. Remember, in nature, gravitational force, electric force and magnetic force are conservative, and their corresponding force fields are conservative force fields. Gravitational field, electric field and magnetic field are conservative force fields. Please remember. Okay, fine. Now we go for question number 3. In this question number 3, we have to prove that closed line integration of electric field over a closed path chosen in the electric field is 0. We have to prove this result. Line integration of electric field taken over a closed path is 0. That is what we have to prove. Let us prove. Look, according to formula, WAB is nothing but line integration of force from A to B. Correct? Similarly, WBA can be written this way: integration of vector f dot vector dl from B to A. Here AB, then here also from A to B. Here it is BA, so here you should write from B to A. Correct? Now, in mathematics, you know, if you interchange the limits of integration, you are supposed to write first negative sign. Okay, come on. When you interchange these two limits, you can write first of all negative sign, minus of integration from a to b vector f dot vector dl. Here lower limit is b, here lower limit is a, here upper limit is a, here upper limit is b. Okay. Now tell me this minus sign as it is, but integration from a to b vector f dot vector dl, integration from a to b vector f dot vector dl, this is nothing but WAB. So this is nothing but WAB, correct? Now tell me, suppose we are moving the test charge from A to B on this path, look, A to C to B, correct? And then after we are moving the same test charge from B to D to A, B to D to A. So we are starting from this initial position, then A to C to B, and ultimately from B to D to A. So we are bringing that test charge back to the same position. In short, we are traversing this, on this closed path. We are traversing on this closed path. Okay, fine. First of all, we go from A to B, then after we go from B to A. If it is so, then you just find out total amount of work done. Let it be W. Total work done on a closed path, let it be W. It should be WAB plus WBA. WAB plus WBA. Come on, transfer this. When you transfer this from minus, it will become plus. So WAB plus WBA. WAB plus WBA. When you transfer this, here it will be 0. So that total amount of work done is 0. Now, you just divide on both the sides by small q. So here it is W upon Q. 0 upon Q will be 0. Tell me, what is this? Amount of work done on a unit positive charge. Amount of work done on a unit positive charge. Amount of work done on a unit positive charge. What was this? This was nothing but line integration of electric field. Line integration of electric field. So this is nothing but line integration of electric field. So it is integration vector E dot vector dl, but we had found out that amount of work done on a closed path. So this is going to give you line integration of electric field over a closed path. You must show this circle. Okay, and that term came out to be 0. Correct? So what we have proved, line integration of electric field taken over a closed path is always 0. Correct? So what do you mean by that? In any electric field, if you choose any closed path of any shape, no problem, but it should be closed path. And then on that closed path, when you move any charge, keeping it under equilibrium, then total amount of work done on that closed path will be 0. Here this total work done is 0. Total work done is 0. Don't you know from 11th standard work energy theorem, W equals to delta K. To know that equals to 0. Change in kinetic energy 0. Change in kinetic energy 0, meaning thereby kinetic energy will remain constant. Kinetic energy will remain constant. Anything remaining constant is said to be conserved. When kinetic energy remains constant, meaning thereby kinetic energy is conserved. Correct? Fine. When kinetic energy is conserved, that's why that electric force is known as conservative force and electric field is known as conservative field. Look, suppose here is uniform electric field this way. Okay? What I do, I just throw a point charge, positive point charge from A to B. I just throw it this way. When I throw it this way, when it moves from A to B, at that time it is constantly acted upon by repulsive electric force in this direction. Though force is towards right hand side, that charge continues to move towards left hand side. At that time that charge will have to do work against that electric force. When charge is doing the work, its kinetic energy will be utilized and so kinetic energy will decrease. Suppose it decreases to 0 at this very point B. For a moment it will come to rest. From second moment onwards, it will be pushed in this direction, this way. At that time it is moving from B to A. Correct? At that time work is done on the charge, and because work is done on the charge, kinetic energy will increase, and by the time it passes through point A, it receives, it gains the same kinetic energy with which it was thrown from point A. What I mean to say, when the charge is moving from A to B and then after from B to A, when it finishes one circulation, when it finishes one round trip in this electric field, its kinetic energy is remaining constant, is getting conserved. That's why this electric field is called conservative force field and electric force is called conservative force. When the charge is moving from here to here, kinetic energy decreases, potential energy increases. When the charge is moving from here to here, potential energy decreases, kinetic energy increases, correct? But when it finishes one circulation, it finishes one round trip on this closed path, when it moves once, then its kinetic energy is getting conserved. That's why electric force is called conservative force and electric field is called conservative force field, okay? Let me give you another example. From this ground surface, suppose you are throwing some body in vertically upward direction. Just at present you neglect air resistance, okay? When you throw that body with some initial kinetic energy, you will notice as the body rises, kinetic energy decreases. At the point of maximum height, kinetic energy becomes 0 for a moment, velocity becomes 0, body comes to rest for a moment. From next moment onwards, it comes downwards, correct? Tell me, when it comes at point A, again kinetic energy becomes equal to initial kinetic energy. So at the end of one round trip, at the end of one closed movement along one closed path, its kinetic energy remains constant, gets conserved. That's why gravitational force is also conservative force and gravitational field is conservative force field, okay? Fine. This is the property of a conservative field, in which if any work is done, it is not going in vain, it is getting stored in the form of potential energy, okay? Fine. Now we go for question number 4 about electrostatic potential, or just for our convenience we speak electric potential, correct? Whether you say electrostatic potential or you say electric potential, we will have same meaning, okay? Actually it is the electric potential to be found out at a particular point in stationary electric field. That's what is called electrostatic potential. But now onwards, for the sake of convenience, we will speak electric potential. See, to understand about electric potential, you just consider a point charge, say charge small q, and surrounding to that charge it has its own electric field. If this is a positive charge, then you know for a positive charge, electric field lines are emerging and going away from it, correct? Come on. Electric field lines are going away from that positive charge this way. Fine. Now tell me, in this electric field, you just consider a point at infinite distance. Suppose this distance is infinite, okay? And at that point, which is at infinite distance, you just consider a test charge, say Q0. Q0 is test charge. Remember the definition of test charge? A point like positive charge whose magnitude tends to 0 is called a test charge. Fine. Now tell me, we would like to have some measure of strength of this electric field, and I told you in chapter number 1, the measure of strength of electric field is given by two quantities. One is vector quantity, which is electric field intensity, and another is scalar physical quantity, which is right now we are studying, that is about electric potential. I am showing you what is that. You just do one thing, you move this test charge, keep it under equilibrium, and then you move it and you bring it at some point, say point P. Now when you move that test charge under equilibrium and when you bring it at point P, by that time you must have done some work against this electric field, because this is positive, this is also positive, these two charges will repel each other, and though this charge repels that test charge, you want to take this test charge closer to this source charge, and for that you need to do some work against this electric field. And amount of work done to bring it from infinity to point P is suppose W from infinity to point P. And you know how to write the work done? Work done can be written by this way. Come on, line integration of force. Line integration of force from infinity to point P. Fine. This W from infinity to point P as it is. This integration as it is. Come on, vector dl also as it is. But mind well, this is the external force which can balance the electric force. Come on, electric force is this way, and if you want to keep this charge under equilibrium, you need to exert some external force which can balance this electric force. So direction of this external force and direction of electric force must be opposite. What is electric force? By formula, charge into electric field, charge into electric field. But because this is the external force which is opposite to electric force, just to show that opposite direction, I just show it here negative sign. This external force you can write this way, minus of Q0 into vector E. I repeat, what is electric force? Charge into electric field, correct? But direction of this external force is opposite to electric force, that's why I am putting here minus sign. Got it? Dot vector dl as it is. Fine. And now take this Q0 in the denominator on the left side. So W from infinity to point P divided by Q0, and minus sign you can take out here, minus integration from infinity to point P vector E dot vector dl. Now tell me, what does this left hand side give you? Here is a ratio, and whenever you see any ratio, you should think of denominator as 1 unit. So this will give me amount of work done on a unit positive charge while bringing it from infinity to a given point inside the given electric field, keeping it under equilibrium. That sort of amount of work done is only defined as electric potential of that electric field at that very point, shown by symbol Vp. Electric potential is shown by symbol V, but because it is at point P, we just write P as a suffix, Vp, that is electrostatic potential at point P. Okay, come on, define it. If this ratio is electric potential, how would you define it? Very simple. In the given electric field, amount of work done on a unit positive charge while bringing it under equilibrium from infinity to a given point against the electric field is called electrostatic potential of that electric field at that very point. I repeat, in a given electric field, amount of work done against that electric field on a unit positive charge while bringing it under equilibrium from infinity to point P is called, infinity to a given point is called electrostatic potential of that field at that very point. Now, from this ratio, you can define this electrostatic potential this way. I am showing you. The amount of work done against given electric field on a unit positive charge while bringing it under equilibrium from infinity to a given point in that field is called electrostatic potential of that field at that very point. I repeat, amount of work to be done against given electric field on a unit positive charge while bringing it under equilibrium from infinity to a given point in that field is called electrostatic potential of that electric field at that very point. last time, amount of work to be done against given electric field on a unit positive charge while bringing it under equilibrium from infinity to a given point in that electric field is called electrostatic potential of that electric field at that very point. Got it? Fine. That was all about the definition. What about SI unit of electrostatic potential? Come on. SI unit of this means SI unit of this divided by SI unit of this. SI unit of work done is joule, SI unit of charge is coulomb, and joule upon coulomb is nothing but volt. Joule upon coulomb is nothing but volt. Correct? Fine. Then what about dimensional formula? Dimensional formula for electrostatic potential means dimensional formula for work done divided by dimensional formula for charge. For amount of work done, come on, what is dimensional formula? M raised to 1, L raised to 2, T raised to minus 2. Here it is. Divided by for charge, come on, A raised to 1, T raised to 1. A raised to 1, T raised to 1. Now simplify. M raised to 1, L raised to 2, T raised to minus 2 minus 1, that is minus 3. A raised to 1 going up will become A raised to minus 1. Got it? Fine. Now, we would like to derive formula for finding electrostatic potential at a point which is at distance r from a given point charge small q. What is that formula? I am showing you the easiest way. Just now we had derived one formula. What was that? WAB is equal to KQQ into bracket 1 upon RB minus 1 upon RA. Remembered? Here it is. This W1 is nothing but amount of work done while moving the test charge small q from A to B. That's why I am putting here symbol WAB, because we move that charge from A to B. Fine. The same right hand side I have written here KQQ into 1 upon RB minus 1 upon RA. Same right hand side you will find here. Correct? Now let us make some changes. Right now this amount of work done is to be replaced by this symbol W infinity to point P, because here initial position was point A, here initial position is at infinite distance. Correct? Then final position earlier it was point B, now final position is point P. Fine. Earlier source charge was capital Q, source charge was capital Q, now the source charge is small q. So instead of capital Q I write small q. Earlier test charge was small q, test charge was small q, and now the test charge is Q0. So instead of Q I should write Q0. The distance of initial position, that is RA, is distance of this point which is infinite. Correct? So RA should be replaced by infinite distance, and this RB means distance of final position. Final position is point P, and distance of this point P from this source charge you can see it is R. So RB is equal to R. Come on, let us make all these changes in this formula. Instead of WAB, I just write W from infinity to point P, small k as it is. Instead of capital Q, I should write small q. Correct? Instead of small q, I should write Q0. Instead of small q, come on, write Q0. Come on, RB should be replaced by R, and RA should be replaced by infinity. RA should be replaced by infinity. And tell me, don't you know 1 upon infinity is 0, and transfer this Q0 in the denominator on the left side, W infinity to point P upon Q0, that equals to KQ upon R, because 1 upon infinity is 0. So left on the right hand side is KQ upon R. Tell me, W from infinity to point P upon Q0. W from infinity to point P upon Q0, what is this ratio? Equal to electrostatic potential at point P. Come on, shown by symbol Vp. So this is nothing but electrostatic potential at point P, shown by symbol Vp. Right hand side as it is. So you have obtained the formula for electrostatic potential at a distance r from point charge small q. Correct? What is the formula? KQ upon R. Okay? Tell me, on which three factors does the value of electrostatic potential depend? Look, it depends on type of medium, because for different media, come on, this value of small k is different. So it depends on type of medium in which source charge is present. It also depends on the value of the source charge, and it depends on the distance of point of observation from the source charge. Okay? So, it depends on these three factors. I repeat, type of medium in which source charge is present, it depends on the value of source charge, and it depends on the distance of point of observation from source charge. Got it? One more thing, this small q is the source charge, but source charge can be positive also, can be negative also. If q is positive, then at all the points inside the electric field surrounding to positive charge, remember values of electrostatic potentials are positive. But if q is negative, then Vp will be minus, that is negative. For all the points in the electric field surrounding to negative charge, values of electrostatic potential are also negative. Okay? Value of electric potential is positive at all the points in the electric field surrounding to positive charge. Value of electric potential is negative at all the points inside the electric field surrounding to negative charge. Remember, if q is positive, then Vp is positive. If q is negative, Vp is negative. Okay? And last point, for a positive charge, this q is positive. As distance r will increase, this potential will decrease. And finally, at infinite distance, when this becomes infinity, something upon infinity will become 0. So, for a positive charge, remember, as you move away from a positive charge, electric potential decreases, and finally at infinite distance it becomes 0. But reverse is the case for negative charge. For a negative charge, value of q is negative. At that time, when you go away from negative charge, this r will increase, but this electric potential will also increase for a negative charge. And then when you go at infinite distance, this becomes infinity, something upon infinity will become 0. So, this will become 0. From negative value, when it becomes 0, meaning thereby electric potential increases. For a positive charge, when you move away from a positive charge, electric potential decreases. For a negative charge, when you move away from it, electric potential increases. For a positive charge, when you move away from it, electric potential decreases. Finally, it becomes 0 at infinite distance. For a negative charge, when you move away from it, electric potential increases, and finally it becomes 0 at infinite distance. Okay? Fine. My dears, please make one point to be noted here. What is that? Here in the definition of electrostatic potential, remember, this amount of work to be done against electric field is minimum amount of work which is done. Minimum. Why? Look, when you want to bring this test charge from infinity to point P, what you are doing? You are simply balancing this electric force. Correct? You are not exerting any additional external force. You are exerting only that much external force which is required to balance this electric force. At that time, you are applying minimum external force, and hence this amount of work done is also minimum. If you desire to bring this test charge from here to here, you can just give it some acceleration also. But when you give it acceleration, at that time you are exerting external force which is over and above this electric force. So, at that time you are doing some extra amount of work. That amount of work is more than this minimum amount of work done. Here in the definition, the amount of work done is, remember, minimum. Okay? And that minimum amount of work is done, and at that time this charge will be moving under equilibrium. Correct? That is with constant speed. Okay?